In this video, you're going to learn about similar shapes. And more specifically, you're going to learn the relationship between the areas of similar shapes as well as the relationship between the volumes of similar shapes. Two shapes are similar if their corresponding linear measurement are in the same ratio and if their corresponding angles are equal. So the corresponding angles have to be equal and the corresponding linear measurement have to be in the same ratio. And I'm going to explain each of these 2 points in more detail shortly. Consider this triangle and this triangle. This triangle has sides with the following lengths. So A1, B1, C1. This triangle A2. So this side, what I'll do is I'll label I'll call this point X, this vertex Y, this vertex Z. I'll do the same thing here, X, Y, and Z. So side XY has a length equal to A1. So A1 is just a variable representing any length. So it could be 10 centimeters for instance. Side XZ here in this triangle. So I'll call this triangle 1. I'll call this triangle 2. Side XZ in triangle 1 has a length of C1. Side YZ in triangle 1 has a length of B1. Side YZ in triangle 2 has a length of B2, and side XZ in triangle 2 has a length of C2. So now let's just focus on the first point I made, which is as follows. For two shapes to be similar, one of the conditions that must be satisfied is that their corresponding linear measurements must be in the same ratio. In this case, the linear measurement we're interested in, or the relevant linear measurement, is the length of any side. So linear measurements, I'll just give you examples of linear measurements. Lengths, heights, the radii of circles. So radii is the plural form of radius, the diameters of circles, and so on. These are linear measurements, the common ones you will encounter. So these are two triangles. They will be similar. Well, the first condition for similarity will be satisfied if A1 divided by A2 is equal to B1 divided by B2, which is equal to C1 divided by C2. So we have corresponding sides. XY and XY here corresponding, XZ and XZ here corresponding sides, YZ here and side YZ in triangle 2 are corresponding sides. You can see that the triangles are oriented the same way. If the ratio of their lengths, or the length of the sides of the triangles, are such that this equation holds, then the first condition for similarity has been met. So I'll just give you an example with real numbers. So here you see a triangle and another triangle. You can see that they have the same orientation. So I'll just label the vertices. Call this X. Call this vertex Y. This vertex Z. Same here, X, Y, and Z. So it's fair to say that side XY in this triangle and side XY in the second triangle are corresponding sides. XZ and XZ in both triangles are corresponding sides, and side YZ and YZ in both triangles, side YZ in both triangles are corresponding sides. So I'll just assign lengths randomly. I'll just call this side with a length of 10 centimeters, here 12, and here just call this 14 centimeters. For this triangle, 5 centimeters, call this 7 centimeters and YZ 7 centimeters. Now, the question now I'm going to ask is as follows. Are these two triangles similar? Or rather, let's even just focus on the first point, the first condition for similarity. Are the corresponding sides of these triangles in the same ratio? So what I'm going to do is find out the following ratio. Well, xy so xy in triangle 1 divided by xy in triangle 2. So the length of side xy. I think too many lines would cause confusion. I'll see if this is equal to the length of side xz in triangle 1 divided by the length of side xz in triangle 2. So this side divided by the length of this side divided by the length of this side must be equal to the length of this side divided by the length of this side, which must also be equal to the length of this side divided by the length of this side. So that's yz in triangle 1 divided by the length of yz in triangle 2. So for these two triangles to stand a chance of being similar, they must meet the condition where their corresponding lengths of the length of the corresponding sides must be in the same ratio. So let's see. Xz in triangle 1, xy in triangle 1 is 10. Xy in triangle 2 is 5. Xz in triangle 1 is this side 12 centimeters, so see that. And xz in triangle 2 is 7 centimeters. YZ in triangle 1 is 14 centimeters, and YZ in triangle 2 is 7 centimeters. So let's see. 10 over 5 is 2. 12 over 7, well, that's 12 over 7. 14 over 7 is 2. 12 over 7 is not 2. So 2 is not equal to this, and 12 over 7 is not equal to 2. So you can definitely tell that the two triangles are not similar. But what if this side now has a length of 6 centimeters? That means that instead of 7 here, we'll have 6. So I'll just get rid of this. Now 12 divided by 6 is 2. So we can say that this condition is satisfied. 10 over 5 is 2, 12 over 6 is 2, 14 over 7 is 2. So the ratio of the length of corresponding sides of these two triangles are in the same, the length of the corresponding sides in triangle 1 and triangle 2 are in the same ratio. Therefore, the first condition for similarity has been met. The second condition for similarity requires that the corresponding angles will be equal. So I'll just call this angle here theta, angle here beta, this angle here alpha. Now angle XYZ in the first triangle must be equal to angle XYZ in the second triangle. So this angle here must also be theta, and this angle here must also be beta, and this angle XZY, so angle XZY, that's the notation, must be alpha in both triangles. So as you can see, the corresponding angles in both triangles are equal here. So given that the lengths of the corresponding sides are in the same ratio and the corresponding angles are equal, these two triangles are similar. In a lot of questions, you'll be told that two shapes are similar. So all you have to do is just work with the assumption that the the shapes are similar and solve whatever problem you're facing. So you have two rectangles, or any two shapes, but I'm just going to use a rectangle to demonstrate an important concept. So this is rectangle 1, and this is rectangle 2. So you know that these two rectangles are similar. You can just pick any side. So I'll call this side, well, the length. So I'll call this L1 and L2. Now, you can easily, or there's a rule that tells you the ratio of the areas of the two rectangles, and I'll show you. So the ratio of the length of the rectangles is L1 over L2, where L1 refers to the length of the larger rectangle and L2 refers to the length of the smaller rectangle. Now the ratio of the area of the larger rectangle to the area of the smaller rectangle is equal to the ratio of the length of the larger rectangle to the ratio of the length of the smaller rectangle, all squared. So in general, if you have two similar shapes, the ratio of the areas of the two shapes is equal to the square of the ratio of the lengths of these shapes. Well, you just have to know that if you're saying, well, the area of shape 1 to the area of shape 2, it's going to be equal to the length of shape 1 to the length of shape, well, the ratio of the length of shape 1 to the length of shape 2, all squared. So shape 1 divided by shape 2, shape 1 divided by shape 2. So just take note of this order. So once you know that two shapes are similar, if you know the ratio of the length or any other linear measurement, you can easily determine the ratio of the areas of the two shapes. Also, if you have two solid shapes, you can deduce the ratio of their volumes. The volume of shape 1 divided by the volume of shape 2 will be equal to the length of shape 1 divided by the length of shape 2 cubed. So say we have, well, two cuboids. So this cuboid 1, just got a 1 here, and another one, a smaller one. Let's call this cuboid 2. Now if you're told that the two cuboids are similar, so the key thing is they must be similar. They're similar, and say you know, well, the height of this cuboid, call this h1, and the height of this cuboid is h2. So that's h2. The ratio of the volumes of the two cuboids is given as follows. So volume of cuboid 1 divided by volume of cuboid 2 is going to be equal to h1 divided the height of cuboid 1 divided by the height of cuboid 2, all cubed. So I use L1 and L2 here just to refer to a linear measurement such as the height. If you had the length, so let's say this was L1, and then this side here is L2, then this equation is true. The volume of cuboid 1 divided by the volume of cuboid 2 is equal to the length of cuboid 1 divided by the length of cuboid 2, all raised to the power of 3. Similarly, if you had this other dimension, which I could call a width, so this would be width 1, and, well, this would be width 2, so that dimension here of that side is with the width of cuboid 1. The volume of cuboid 1 divided by the volume of cuboid 2 is equal to the width of cuboid 1 divided by the width of cuboid 2, all cubed. This applies when you have two shapes that are similar. Of course, volume, you're only going to be talking about volume when you're dealing with a solid shape like a cuboid or a cylinder. So just keep this in mind, and we're going to try out some examples now and apply what we've just learned. Here's an example. It says, the lengths of the hypotenuses of two similar right angle triangles are in the ratio 2 to 5. What is the ratio of the area of the larger triangle to that of the smaller triangle? So we have two right angle triangles and they are similar. So I'll just roughly sketch two right angle triangles. One's bigger than the other. So these two triangles are similar. And we're told that the hypotenuses, so this is the right angle. This side here is the hypotenuse, the side opposite the right angle. So I'll just define its length as, I'll just call it L1. And this, the hypotenuse, the length of this hypotenuse, I'll call it L2. We're told that the lengths of the hypotenuses are in the ratio 2 to 5. That means that the length of the L1 divided by L2 is equal to 2 over 5, or L2 divided by L1 is equal to 5 over 2. How did I do that? Well, this from my sketch, I'm specifying that triangle 1 is smaller than triangle 2. Therefore, in this ratio, this 2 here, or let me put it this way, ratio of L1 over L2, if L1 over L2 is 2 over 5, that means that L1 refers to the smaller length and L2 refers to the larger length. For L1 over L2 to be 2 over 5, L1 has to be smaller than L2. That's the meaning of this equation here. And here, for L2 over L1 to be equal to 5 over 2, L2 must refer to the length of the hypotenuse of the larger triangle. Just think about it. If the length of a square, of the one square is x1, and I call that, well, 10 centimeters, and the length of another square is 20 centimeters. Now, x1 over x2 is 10 over 20, which is 1 over 2. As you can see, this, because the numerator is smaller than the denominator, it means that x1 must refer to the smaller square. In this case, that smaller square has a length of 10 centimeters, as you can see. If I wrote x2 over x1, if I try to find the ratio here, it would be 20 divided by 10, which is 2 over 1. As you can see, when I take the ratio of the the length of the larger square to the length of the smaller square, I get a fraction where the numerator is larger than the denominator. Here, when I take the ratio of the length of the smaller square to the length of the larger square, I get a fraction whose numerator is smaller than its denominator. So just be careful with that. Now, because the two shapes are similar, I know that the area of shape 1, the ratio of the area of shape 1 to the area of shape 2, so triangle 2, is equal to the length of triangle 1 divided by the length of triangle 2, all squared. Which means that the area of triangle 1 divided by the area of triangle 2 is equal to 2 over 5 all squared. So I'll just continue down here. That's equal to 4 over 25. So 2 over 5 all squared is the same thing as 2 squared divided by 5 squared. If you don't know why, I'll just quickly review the following law. X over y to the power of n is equal to x to the n divided by y to the n. So x to the n divided by y to the n. And that's what I've applied here. So the area of the smaller triangle to the area, well, the ratio of the area of the smaller triangle to that of the larger triangle is 4 over 25. But we'll ask for the ratio of the area of the larger triangle to that of the smaller triangle. So A2 over A1, which is simply 25 over 4. You just take the reciprocal of both sides of this equation, and this gives this. Therefore, the area of the larger triangle, the ratio of the area of the larger triangle to that of the smaller triangle is 25 to 4. And that's all. So here's another example question, and it says the areas of two circles are in the ratio 9 to 16. What is the ratio of their diameters and radii? Now we have two circles, and one thing you should keep in mind is that circles are similar shapes. And I'm not going to prove it here, but I'll just like you to accept that. So circles are similar shapes. Now we're told that we're given the ratio of their areas and required to find the ratio of their diameters. You need to realize that a diameter is a linear measurement, a radius is also a linear measurement, and a rule of thumb to determine if something is a linear measure, a dimension is a linear measurement, is just to see if you can measure that dimension with a ruler or a tape rule or a meter rule. If you can do that, then the dimension is a linear measurement. So a diameter is a linear measurement and a radius is also a linear measurement. And from what we've learned, we know that if two shapes are similar, the area of shape 1 divided by the area of shape 2 is equal to a linear measurement of shape 1 divided by a corresponding linear measurement of shape 2 all squared. So that means that, so what this means is that the area of shape 1 divided by the area of shape 2 is equal to the radius of shape 1 divided by the radius of shape 2 all squared. It also means that the area of shape 1 divided by the area of shape 2 is equal to the diameter of shape 1 divided by the diameter of shape 2 all squared. So what we know so far is that the ratio of the two shapes, or the areas of the two shapes, is given as 9 to 16. So I'm just going to call shape 1 the smaller shape, and well, circle 1 the smaller circle and circle 2 the larger one. I'll just assume that. So the area of circle 1 divided by the area of circle 2 is equal to 9 over 16. So let's try and find the ratio of the radii and the ratio of the diameters. So A1 over A2 is 9 over 16. And we've said that A1 over A2 is equal to R1 divided by R2 all squared. This means that R1 over R2 all squared is equal to A1 divided by A2. And that means that R1, so the radius of circle 1 divided by the radius of circle 2 all squared is equal to 9 over 16. So A1 over A2, 9 over 16. And that means that I can determine R1 over R2 by taking the square root of both sides of this equation. Taking the square root of the left hand side gives R1 divided by R2. Taking the square root of the right hand side gives the square root of 9 over 16, which is equal to the square root of 9 divided by the square root of 16. So the radius of circle 1 divided by the radius of circle 2 is equal to the square root of 9, 3, divided by the square root of 4, which is square root of 16, which is 4. So the ratio of the radius of circle 1 to the radius of circle 2 is 3 to the 4. And because the diameter is also another linear measurement, the ratio of diameter of the first circle to the ratio of the diameter of the second circle is also going to be 3 to 4. So what you could do is just replace R1 over R2 with D1 over D2 here and see if you get the same result. Of course you would, because all we're just saying is the ratio of the area of a shape to the area of a similar shape is equal to the ratio of a linear measurement in shape 1 to a corresponding linear measurement in shape 2 all squared. So diameters will have the same ratio as the radii. Here's another example. It says the sides of two cubes are in a ratio 1 to 3. Given that the smaller cube has a volume of 64 centimeter cubed, find the volume of the larger cube. So we have two cubes. I'll just sketch Give you a rough sketch. So this is just one cube, and then there's another one which is larger. It's just a rough sketch. We're told that the sides of the cubes are in the ratio 1 to 3, so the length of the side. So as you know, for a cube all the sides have the same length. So this just means that L1 divided by L2 is 1 over 3. So if this is shape 1, the smaller cube with sides of length L1, and this is cube 2 with sides of length L2, this ratio holds. L1 over L2 is 1 over 3. So given that the smaller cube has a volume of 64 centimeter cube, so we're told that the smaller cube, which is cube 1, V1 is 64 centimeter cube. We're required to find the volume of the larger cube, V2. How do I go about this? Well, what you know about similar solids is as follows. The volume of a shape divided by the volume of a similar shape is equal to a linear measurement of the first shape divided by a corresponding linear measurement of the second shape, all cubed. Now, cubes are similar, and that's simply because all the corresponding sides of two cubes will always be in the same ratio, and the corresponding angles will be equal. And I'll demonstrate that shortly, but let's just proceed. So accept that cubes are similar shapes, and given that, you know that the volume of cube 1 divided by the volume of cube 2 is equal to L1 over L2 all cubed. So that's 1 over 3 all cubed, which is equal to 1 cubed, which is 1, divided by 3 cubed, which is 27. So we know that V1 over V2 is 1 over 27. And we know that V1 is 64, so 64 cm cubed divided by V2 is 1 divided by 27. So cross multiplying will give that V2, I'll just do that here, V2 is equal to 64 times 27. And that means that V2 is equal to 1,728 centimeters cubed. I mentioned that cubes are similar shapes, and I'm going to show you why. So here's one cube here, and this is a cube with sides of length 10 centimeters. So all the sides have a length of 10 centimeters. It's a cube. So these are the key dimensions, this, and that. And here's another one, which is bigger. All its sides, so this is just a sketch, rough sketch. All its sides have a length of 20 centimeters. So this is what I'll do. What I'm saying is dimension is 10, this dimension is 10 centimeters, this dimension is 10 centimeters. I'm just not showing the units. So I'll call this vertex B, this vertex C, this vertex D. And for the second cube, call this vertex A prime, this vertex B prime, this vertex C prime, and this vertex D prime. So the corresponding sides, AB, and then A prime, B prime, BC, B prime, C prime, BD, B prime, D prime, are in the same ratio as you see. So AB, the length of side AB divided by the length of side A prime, B prime is going to be equal to the length of side BC divided by the length of side B prime, C prime. That's also equal to the length of side BD divided by the length of side B prime D prime. The length of side AB is 10, A prime B prime has a length of 20, BC has a length of 10 centimeters, B prime C prime has a length of 20 centimeters, side BD has a length of 10 centimeters, and side B prime D prime has a length of 20 centimeters. As you can see, this ratio is 1 over 2, this is 1 over 2, this is 1 over 2. So the corresponding sides are in the same ratio, so that's one of the conditions for similarity. And the other condition is that the corresponding angles must be equal. This angle is all the angles between sides that meet are at 90-degree angles for a cube. So I'm just going to show some. All these angles are all 90 degrees. So the corresponding angles are also equal. So any two cubes will meet the conditions for similarity, which is why the question we just solved was based on the assumption that, we just took, based on the assumption that the cubes are similar. The question didn't state that the cubes were similar. We just knew for a fact that cubes are similar, and I've just shown you why. So it's not an assumption, but it's something you should know. So just make sure you always remember that any two cubes are similar, which means that the volume of one cube divided by the volume of another cube is going to be equal to the length of the first cube divided by the length of the second cube, all raised to the power of 3.